Okay, so I got my plasma cutter all apart here on the workbench, aka the kitchen table, and I figure while I'm at it trying to fix it, may as well show you how it works. This is the base part of it here. And it's pretty interesting the way these things work. Anyway, you got your, this is the mains coming in here, and that goes into a switch, your main power switch here on the front, and you can see it there, that's the front there. And from there, there's a couple black wires that are kind of hard to see in this light, crummy light in here, but anyway, they go back into this circuit board here with all these big, well, they're not very big, but as far as capacitors go, maybe the ones you've seen, compared to them, they're big, but into there, and there's a couple connectors here. It goes into there first, and those connectors, they go into these. Get my finger in the right place here. Anyway, could make a joke on that. I'm not going to go there, but they go into these. There's two of them on the bottom here, bridge rectifiers, and those take the AC. You can see that there, and they convert it into plus, and on the other side there's a negative or minus, and then that goes, to these capacitors here that we were looking at a minute ago, and those smooth it out, and you get a nice, more or less, you get a nice DC. Like a battery, what you get from a battery. Except in this case, it's 330 volts. And there's actually some smart, in this one, there's some smart circuitry in here that has to do with these relays, these blue things here, big relays. Well, like I said, everything's relative. These aren't big as far as relays go. These are just like babies. They get so big, but anyway, these and the associated circuitry, there's like a little low voltage power supply in this area, and it's got a so-called smart circuit in here that takes you could use 120 or 240 volts, and using these relays, it switches that so that you always get 330 volts DC out of these capacitors. And this is the cord here that goes up to your up to the main drain up there, the main circuit board. Anyway, and yeah, this is the 330 volts. They used a bunch of wires on here, because this little connector here, each pin can only handle so much current, so they used 3 of them for each rail. Yeah, 3 for negative, 3 for positive, to spread out the current so it could handle, however many, probably 20 amps. Current into there, and yeah, this I was showing you a minute ago. This is the low voltage one. There's 2 of them actually. This is the smaller low voltage power supply, and this runs the fan. We got a cooling fan here, kind of hard to see in the dark anyway, and it also runs down here, another hard to see, but you can see the air hose goes into this. This is the solenoid valve that gets your air coming and going. And you can see the air hose goes to the front here, where your hose to your torch connects, and that switches the gas on and off, the air, or you know, you could run it from just like plain nitrogen, and I guess you could get a better arc and stuff. But that's probably not what you're going to be doing, you know, in your home shop, because that can get kind of expensive. But you know, they run like nitrogen or even like argon sometimes in the big manufacturers, you know, on their plasma cutters to give better arcs and better characteristics to the arc or whatever. So anyway, that pretty much sums up this entire board here. And this is actually, it's kind of hard to see, but you know, this is a board, one board over here, and this is another circuit board, a completely separate circuit board here. And then this here is just a little circuit board with a toroidal transformer, or I think that's just a filter choke actually there, and that's just connected right to this main output terminal here. This goes to the other. This is where the ground clamp connects, and or no, I'm sorry. This is the switch. This goes to the switch on your torch, you know, to get the you know, the air and the power coming and going. So that's what that little circuit board over there is. Anyway, we'll get more into this one in a minute. First, though, I want to explain this over here. And if you notice, there's two circuit boards. Actually, there's one up here, and there's one down here. And the one up here is basically, well, this one has a little daughter board here, and this is the main control circuit here that switches all these big transistors on and off. And this one down here, this is the just the transformers and diode rectifiers down here, and you know, filter. Got a couple big heavy-duty DC filter chokes with those are probably iron powder toroidal chokes there. And then this here, this coil here is let me get a better angle. Sorry, I'm just shaking all over, I know, but anyway, this is the what is this? This is the arc starter, the H high frequency here, and this is the primary here. This is a primary. It's like a transformer, but it is a transformer. And the primary wraps around in there between, if you can see that, between the windings of the secondary, which is this big, thick copper strap here. It's got to be real thick to carry all that current. The full cutting, you know, current is formed through this. So it's got to be real thick. All right, now we'll get more into that later, but right now we're going to focus on this. Right here, this chip here, that's your main pulse width modulation chip right there. And the part number on this particular no, not a welder. It's not a welder. It's a plasma cutter. What is it? Plasma cutter. Anyway, this is the the part number is SG3525. And if you know anything about PWM and the, you know, chips and everything, it's a pretty good chip. It's you know, it's one of the higher end chips actually. And I think this one here is actually made by, I think it's made by Fairchild, one of the better manufacturers. It's got an F on it. That could be Fairchild or I forget who the other one is that uses an F in their logo. But anyway, this is your main control chip here. And this is what tells the big transistors here what to do, when to come on and turn on and off. It goes to these four. This chip, first of all, there's like 3 stages in this. The first stage is in here. This is the chip that controls all the signals and everything. Then that goes into these 4 little transistors here. And that's just basically to increase the current output. Because when you're switching these MOSFET, these are known as MOSFET transistors here, these big ones. All the current is drawn in the actual switching, you know, on and off. And when you're doing that like 250,000 times a second, which is the frequency of this unit here is about 250 kilohertz, that you know, it starts to draw a lot of power. So this is the first stage here, these 4 little transistors, and that gives more current output than just this would. And then after that, there's actually another stage before we get to our real big transistors, and you can just see it. There's 4 copper colored things here, and those are the actual gate drive transistors, and they're a little bigger than these little ones here. They're kind of an in-between size, and they go into this cable here, which if you follow it goes to this. This is the gate drive transformer, and this is what actually goes to all the MOSFET high power transistors, you know, the big ones. They're big. They're on this heatsink, this big heatsink. It's actually, there's 2 of them. There's a heatsink on this side, and there's another heatsink over here on this side. And the fan blows the air in here between the 2 heat sinks. It's kind of like the, you know, they call it, the Miller calls it the wind tunnel. It's kind of like that. And you can kind of see the, one of the main power transformers in there. And it blows the air over all that stuff. So anyway, back to our gate drive transformer. This you know, the gate of the MOSFET, these big transistors here, if I can get it in the picture, is what switches it on and off. You know, if you think of a gate like the gate in a fence, you know, you open and close that to let your cows or your sheep or whatever, or your kids come and go, and your monkeys or your zebras or whatever. And so that's what actually turns the transistor on and off, is the little signal on the gate. Makes a really big signal come out of the not the collector. That's the other kind of transistor. The drain. The drain. It allows the current to flow between the source and the drain, and turns it on and off. And you probably, that's kind of hard to see. There's junk in the way, but on this one we actually have our transistors in what they call a full bridge arrangement, where there's 4 transistors. Actually, they have them in 3s here. So there's actually 12 transistors. And that's part of the reason too why they need such a big gate drive transformer and these big MOSFETs here to drive the gates, is just because there's just so many gates to drive. And you know, I don't know why they went with this design. You know, the American units, you know, they use just a couple really big transistors in theirs, but I don't know. Anyway, you know, they had it all planned out to mount it in this way, you know, and you know, it works, whatever, you know, it sort of works anyway, except when it blows up like mine did. Anyway, so the way this gate drive transformer is connected, it'll switch this configuration called an H bridge. Two of the sets of transistors will come on at a time. So these two sets here, these 6, and I'm not exactly sure. It might be these 6, or it might be these 6, or you know, it's either diagonal or just straight across like this, or you know, it could even be like this, these 6 and these 6. But anyway, it doesn't really matter for our illustration purposes. 6 of these, or you know, if you just have 2, of course it'd just be 2 would come on, or I mean 4. Anyway, I don't want to get you too confused, but these will come on, and then in the next part of the cycle, or I guess you could call it a cycle, these 2 will come on, and then they'll go off and these 2 will come on again, and they'll just alternate like that, back and forth, thousands of times every second. In this case, this is 250 kilohertz, so 250,000 times every second. And they're arranged in such a way that your wires, output wires coming out of here, just imagine that there is one red and one black, because this is just, I'll get more into it, but there's just, imagine there's just a red and a black, you know, that's your positive and your negative, or whatever. Except this is converting DC into AC, back into AC. Except at a very high frequency. So that way we can convert our wall voltage, our high voltage, low current into a lower voltage and a higher current. That's what the whole purpose of this is, and a controlled current too at the same time, so that we don't, you know, otherwise if you just leave it without current control, and we'll get more into the current control later, it'll just, you know, overload. It'll just, the current wants to just run away with itself. Anyway, these white things here, and these white, you notice there's one blue thing for every big white thing, are this is a big resistor, and this is a capacitor, and together these two are in series, and there's 4 of them, one for each set of 3 transistors. These are called a snubber network, and what that does is, since we are switching into an inductive load, the transformers down in here, these yellow things that are hard to see in here, and there's 3 of those. Because we're switching into an inductive load, we have spikes of high voltage that will come back from those transformers. So this will absorb that. The capacitor and the resistor will absorb that spike. And that's called a snubber network. Continuing on, so now we have our high frequency AC switching back and forth here. And that then goes into these 3 capacitors. Or, you know, 6 actually. There's these little, these are ceramic, these blue ones. And then these are like polyester or, you know, what do they call that stuff? There's different names for it. It all refers to the same thing. You know, there's polyester and there's polypropylene, which is another kind. But these here are polyester. Maybe I'll remember the other name for it later. But anyway, each one of these red ones is connected in parallel with one of these blue ones, and that you might wonder why they do that. Well, the blue ones have lower resistance than the red ones because they're ceramic. The ceramic has less internal resistance than the polyester, whatever I just said. Anyway, 2 of those go here to the output transformers, the big ones. And the other 2 go to this other connector, which is currently not connected. And that goes to the high frequency board. And that runs the high frequency board. That is what starts your arc. It has a high voltage, high frequency. And we'll get more into that later. Okay, so anyway, going along our signal path now, we've gone through these capacitors, and what these do, I didn't say what they do. What they do is they basically they're just a safety measure. Actually, it depends on it depends a lot, but I'm not exactly sure on exactly the way this circuit is laid out. But they filter out the any DC which might get in here. You know, say one of these, or maybe 2 of them, or maybe even all 4, which would be really bad, will get stuck on for some reason. You know, that would be a fault condition, what they refer to as a fault condition. Say that happens, this will prevent the DC from going into the primary coil of the transformer, and you know, potentially burning that transformer out. You know, you're at that point, you know, your transistor is probably already gone. So, you know, but that prevents like a big fire and explosion from happening in here. And it's mostly safety. But you know, it may actually, depending on how this is laid out, this may even be an essential thing to have in this circuit, where there's always, you know, sometimes there's always going to be a DC component to your switching, and this would just block that, because the coil in the transformer you don't want that getting into the coil of your transformer for a number of reasons. You know, first of all, that could you know, burn it out. You know, just from too much current, and also it could cause what they call saturation of the transformer core, and that's bad. You don't want that. You don't want that. And that'll burn it out too. That'll cause too much current to flow in there and burn out your transformer. So, you know, DC is bad in a transformer. Usually, usually, if it's not pulsing, it can be bad. And that just helps, safety, or, like I said. But I'm pretty sure this circuit is just like a safety feature, because this is a full bridge circuit. You have 4 transistors switching like that. It's just your safety, to keep stuff from, going real bad. Anyway, here we go. We're going finally. All right, I'm done with this board. We're pretty much done with this whole board. I mean, there is this. This is another big transistor. This is, I didn't talk about this. I should do that now. This is another big transistor here, and that switches into this little transformer here, and that is just the low voltage power supply for this control circuitry to control the gates of the main transistors. And there's 2 of these. I showed you the other one already in the input board, power input board. This one here just only does this. It doesn't do the fan. The other one does the fan and the relay, the solenoid, the valve, the solenoid valve. This just does what's here. So anyway, so we're going to the transformers. Now these step down the voltage, and at the same time, because you're stepping down the voltage, the current has to increase. Your potential for current increases. So we have a lot of primary windings in there, and then a few big, thick secondary windings. And then, it's basically that. Then it just turns into, a simple rectifier circuit. And these are your diodes here, your rectifier diodes. And once again, there are 12 of those. I don't know why, but anyway, and there are 3 of these transformers, and these transformers are they're hard. You can't really see. I don't want to take this all apart again. I should have probably done this when I had it all apart, but anyway, it's probably easier to understand this way. These are just like a regular computer power supply type transformer, ferrite core transformer. And there's 3 of them in there. You can't see them, but you can see the 6 wires coming out here. 2 wires for each primary winding in each of the 3 transformers. Okay. And then, the diodes, those, if you don't already know, those will turn, they're just like these big ones here that I showed you before. They're not just like, anyway, they're similar. Except these are high frequency. These are special high frequency diodes. You can't just run any old diode in here. Otherwise, bad things will happen. The lighting in here is just real bad. But anyway, there's little black things on each one of the legs of the rectifier diodes, and there's 2 diodes in each package. They call these black, diode things packages. And there's 2 diodes in each diode. There's 2 in that one, there's 2 in that one, there's 2 in that one, and so on. And convert the alternating current from the high frequency alternating current from the transformers into a high, a DC, and direct current, convert it into direct current, and they steer that into direct current. And the black things on the legs that are really hard to see are what they call ferrite beads, and those are there to absorb like really high frequency to keep that out of the circuit. And because when these diodes turn on and off, there could be an even higher frequency component, and you don't want that. So they put a little ferrite bead on each leg of each of these diode packages, rectifier units here. And after the diodes, now we have a pulsing DC direct current signal, and I mean, it's really, really high current. It's at least 50 amps probably, and you can see how they soldered over these traces on here because of all that current. There's just a big heavy patch of solder over these. And they also put in copper. I'm getting tired. I'm sorry. A copper wire, a big copper wire across to help carry the current. And that heavy current then goes into these, which we saw before. These two big filter chokes. And what these do is they take that pulsing high frequency and they help to smooth it out, so it's not it's more like a regular DC, like from a battery, than a high frequency pulsing current. And They could have even gone and put capacitors on here, but they didn't. And here's why. When you put a capacitor on there, it's impossible to regulate. It becomes impossible to regulate your current. So they left those out because the capacitor will charge up, and then when you make when you start your arc, that capacitor will discharge into your arc and just make a big mess, big high current pulse. So there's no capacitors here to filter this, just these two big chokes, and each choke is coming from one is like the negative rail and the other is the positive rail. And apparently they felt they had to use two of them because one of them would have been, it would have been bigger than, probably bigger than any core, wouldn't have fit on any core that material they could get their hands on. And because these are about, the biggest, you can go bigger, but these are about the biggest, you can reasonably get, at a cheap price. And this thing is all about the cheap. So that's why they went with two instead of just one big one. And then after that, after these two, you have some little capacitors and a little inductor and stuff. And there's MOVs in there too, and that. I won't get into those, that's a whole nother story, but that basically prevents like high voltage, that's these big blue things here, that prevents really high voltage spikes from making it through to the work and doing bad things that you don't want them to do. And it also helps protect some of the other circuit boards, because then and I don't think you can see it, but there's a current sense shunt. Okay, you can kind of see it. It's this thing back here, and after it comes out of these filter chokes, it goes through this, and this is basically a resistance, and a voltage will will form on that resistance, and that voltage is directly proportional to the current flowing through this circuit. And that's why it's called the current sense shunt. And it goes into this connector here and back up to this connector here on our control board, our main board, and it goes into the control board and everything. And to feed back the current, the amount of current into the control circuit, so that it can adjust the pulse width, or in other words, how long these all here stay on, in order to limit the current. Otherwise, everything would just, blow up, and and you don't want that, of course. And so it comes in here, the current signal, the current feedback signal from the shunt comes up here through that connector, then through that connector, and then into here. And this, it goes first into this, I believe, and I'm still trying to figure this out, because this current sense circuit is what went bad on my welder. Here I go again, calling it a welder. On my plasma cutter, this is what went bad, this current sense circuit. And there's actually two of them. There's another one here. This is a current transformer. That's another way to sense current in a circuit. And this is connected directly to the main transistors here to sense the current that's actually going into the whole thing here. And it's basically, it takes a high current signal here and it turns it into a lower, converts it into a lower current signal here, and then this takes that current, these four diodes here rectify that, turn it into DC, and then these resistors here, not that gray one, these blue ones, turn that current, convert that current into a voltage, and that voltage is then sent back here to this, once again, to your main control board. And that's another way to sense current. But the main current sense is from the shunt here, this shunt, this thing here. And it goes, that one, that is just an auxiliary, that's for safety, once again. The shunt goes into this here, this little chip here, and this is what they refer to as an op-amp, or an operational amplifier. And it's pretty complicated. This control circuit is the most complicated part of the whole circuit, is right here. And so it gets complicated. Basically, this op-amp senses the current and adjusts and it tells this chip over here, the pulse width modulator, how wide of a pulse that it should give to get your current set from your set point from the knob on the front of the machine. The knob plugs in there. And that's a potentiometer, variable resistance. That plugs in here. That and then there's some trim resistors here that helps to calibrate that front panel knob to make sure that you're getting exactly what current you set on the front, because there's variations. Every component is different. This compensates for that, these trimmers here. And that's basically it. That's pretty much it. that's pretty much how it works. So anyway, you know, now that we've gone through and we've explained all this stuff, we can recap, you know. So the power comes in here, and then you know, these are a couple more filter capacitors anyway. You know, smooths it out so it's more like DC, and then it goes into these big ones. These big ones switch on and off like that, and you know, they're controlled by this. And the amount of time they stay on, you know, they'll be on. These two will be on, and then they'll just shut completely off, and none of them will be on. And then these two will come on, and then they'll all shut off again. And the time they stay on is controlled by how much current is flowing through here, and then that goes into our transformers that step it down to a low voltage that's then rectified by these diodes here, diodes into DC, direct current, and then filtered by these big chokes, and then through, that's what I forgot, that's what I haven't done yet, the HF, high frequency, goes through this coil here, and then to your torch. Okay, so you might be wondering, well, you know, this is all low voltage, this is such a low voltage, you know, how do you start an arc with such a low voltage? Well, that's why you have this. This is the HF transformer here, and the input, you know, the primary goes to this board over here, and this is what they call a flyback transformer here. And I don't know, you know, some of you might be familiar with the television and how that works. Well, this is the same thing as a television flyback transformer. It you know, takes a lower voltage, higher current, and steps it up into a high voltage, low current. Okay, and this is the input. And it piggybacks off of the big main power transistors up there, and that was that other connector. That was this connector right here, and then it goes into this choke here. This is a current limiting choke to limit how much current goes into the primary of this flyback transformer. And then after the transformer steps that you know, 330 volts up to maybe 10,000 volts, it goes into a couple little yellow capacitors here, and these it'll charge these up. They charge up pretty fast because they're small. And when they get all charged up to enough voltage to break down this, there's a spark gap here. It's hard to see, but there is a spark gap there. Then that'll break down into that spark gap and discharge those capacitors, those little yellow capacitors, into the primary of this coil, this transformer here. And since the secondary is in series with our torch, that high voltage from those capacitors will be superimposed onto the low voltage from the high current, low voltage from here, and that is what will get your arc started. So it just it's basically it's similar, very similar to a Tesla coil, except the it's just low voltage here. Well, it's high voltage. What am I trying to say? This is like a Tesla coil primary here, like two primaries wrapped around the same core, and this will be, and it takes the high voltage and puts it to your torch. Anyway, I'm getting kind of tired and worn out. I've just done 2 videos, so I hope this is good enough so you can understand. Maybe some of you who know less about this stuff can understand what I'm trying to say. It's not that hard. It's not that hard, difficult to understand. Once you're get past the initial learning curve, it's pretty simple. So that's pretty much it. We did the voltage input board, the high frequency, the main board, and the rectifier and transformer board, the high current board. So that's pretty much how it works. And I hope that was understandable for most of my viewers. So yeah, that's how a plasma cutter works. And yeah, thanks for watching. Have a nice day.